we have this equation when calculating the gradient, which is delta y divided by delta x, the change in y divided by the change in x. How much does y change for every change in x? And if you utilize function notation, you end up with fx plus h minus fx instead of delta y, and h instead of delta x. And instead of probably is not the right phrase, it is the equivalent of, but when analyzing, when describing a graph in terms of function notation. Now let's start using it to see if it is true, if it manifests actual calculations of gradients to the same degree we would get if we put a ruler on the page and worked out change in y and worked out change in x and then did a division. So for example, we've looked at fx equals 2x. We had it in the form y equals 2x in the last video we had. Now for y equals 2x, we are aware that we were able to compare it to such things as y equals mx plus c, and both visually and by analyzing this equation, we were able to say that the gradient m was 2. Change in y divided by change in x was 2. And so if this is true, if this equation is the equivalent of change in y divided by change in x, we should calculate a gradient of 2 for this function fx equals 2x. That is to say, fx is if you hopefully you are comfortable with the idea that fx is equivalent to y. This is a Cartesian way of putting this. This is a function notation version, which is a little bit more powerful with regards to calculus. And the 2x, of course, is just 2x. So let's try that. Let's see what happens if we find the gradient of fx equals 2x by way of this equation. Does it give us the gradient of 2 that we desire? So let's look at this. So the first thing we're aware of is fx is 2. So if I'm going to do the equation, I can literally remove fx and just put 2x, not 2, sorry, 2x. So this, I can just say, well, I already know that fx is 2x because y is equivalent of fx and y equals 2x. So fx equals 2x as well. So I'm going to just be able to put 2x in here. H, we'll have to deal with it at another time. Fx plus h is where individuals tend to get stuck at this point. It would be to what on earth is fx plus h? Fx perhaps is quite comfortable, but fx plus h is slightly strange. Well, fx plus h just means that instead of x, we are going to plug in x plus h. So you see here, I have x. Now I'm going to put in x plus h. And so, therefore, instead of 2x, I'm going to put 2 multiplied by x plus h. This can be done quite comfortably by doing 2 multiplied by x first, followed by 2 multiplied by h, leaving me with 2x plus 2h. So if someone were to ask for the function fx equals 2x, or y equals 2x if that's what you're more comfortable with, the answer of what fx is 2x, and the answer for what fx plus h is 2x plus 2h. And I'm hoping that I broke that down into enough steps for you to know how I got to that. So therefore I can substitute this in. First of all, there's an fx plus h in my formula, so instead I'm going to put 2x plus 2h. There's an fx in my formula, and as discussed, I'm going to move that and convert it or substitute it, for want of a better phrase, to 2x, because we're aware of that as discussed earlier. Now, what does that leave me with? It leaves me with this formula here, 2x plus 2h minus 2x. And of course, you may be able to see certain things manifest, like 2x minus 2x is 0x, leaving me with 2h over h. The h's cancel, and we get exactly what we wanted, which was 2. dy by dx, or delta y divided by delta x, is 2. And that is exactly what we thought, because if you utilize the idea that this is a straight line, y equals mx plus c, the gradient was 2. So our formula works for straight lines. Now, this is advantageous. We know it now works for straight lines, but does it work for curves? So what I've said we now need to analyze is, does it work for y equals x squared? So that's what we'll look at next. So if you take a look at this, we have fx equals x squared. So again, be aware, if depending on your comfortability with function notation, this is the equivalent of y equals x squared. And so I'm going to write fx equals x squared. I'm going to utilize that in my formula later for the fx part. for fx plus h. Well, what would that be? Well, here is the thing again. Let's make sure we drive this home. Instead of x, it is x plus h. So wherein we have x squared, we now have x plus h, all squared. This is the equivalent of x plus h times x plus h, or we can use Pascal's triangle to expand this. I can expand this in steps. If we wish, we can say this is x times x is x squared, x times h is hx, h times x is hx, and h times h is hh. Thank you for bearing with me on that one. We get x squared plus hx plus hx plus h squared, and therefore this is our fx plus h. But of course we can bring these together. There's no requirement to not realize these are two of the same species. So it'll be one apple plus two apples, one apple plus one apple is two apples. We get 2hx. So I'm going to use this, and you see how I'm going to use it is as follows. Note how I have fx plus h in my equation. This is the equation for the gradient. Let's not forget that is my equation for the gradient, fx plus h minus fx of h. Instead of fx plus h, I'm going to put in x squared plus 2hx plus h squared. And instead of fx, we know I just simply need to put in what that is, which is the equivalent of y, as y equals x squared. So in here, I'm going to put x squared. Then I'm going to have to do a little bit of simplifying. Well, one thing I can do straight away is x squared. Take away x squared is 0. Now, let's analyze this in a little bit more detail. What do we have here? We have 2hx plus h squared, and it is all, at this point in time, it is all divided by h. That's what we have here. Let's analyze this, make it slightly bigger. That is what we're concentrating on. It is all divided by h. So what can we do with this? Well, let's look at this in a bit more detail over here. First of all, we can break things down or cancel things down. The division by h, because these both have h in them, this h is going to cancel with this one. And this h squared is going, which is h times h, is also going to cancel. What would it produce? It will produce instead, this will give me 2x plus h, like follows. Now, of course, just to make this or make you aware, that is because h squared is equivalent of h times h. So if I have h divided by h, one of those h's will disappear. And so that's what gives me this h. And 2hx divided by h, the h disappears. So that is what I have, 2x plus h, 2x plus h. Now the problem with this would be that there is an h in here for which many individuals will not be sure what to do with. What is h? First of all, let's make sure we're well aware of what h is. H is the length of change in x. The change in x is h. So one thing to analyze is that we can see there is some issue with regards to our concept here. The gradient, which can be ran at, or the tangent at this point, the gradient at 1, is very accurate when you zoom in and you have a very small situation to analyze. But as you zoom out, you can see that there is issues in this gradient, mainly because there is a gap that builds up between here on this side, and you can see the equivalent happens here on this side. And we can say therefore that the larger we make our triangle and analyze the change in y relative to change in x, the more there might be the probability of error. Now, of error occurring. So what I could do instead is I could zoom in and make my triangle, I'm zooming out in and out far too much there, perhaps making individuals feel slightly nauseous, but what I could do is instead I can produce a triangle that's extraordinarily small, so that would be my gradient there. And then from there, I can work out the change in y by just doing that as my change in y. And this triangle will be particularly small because I will be making it such that the h, this length, the change in x, is small. How small? Well, the smaller the better. And this we can describe this, the smaller the better concept as, when discussing this, we can describe it as, let's try and make this so that the h goes to 0. We're going to try and make it so that that h goes to 0, leaving us only with 2x. All we get, therefore, as a result is the 2x. So if I go back here and neaten this up somewhat, what we can say is that there is no requirement then to have the h in our final equation. This breaks down into 2hx over h. There's technically a plus h missing here. Let's plug that in. There's a plus h missing. Let's sort this out. Let's plug this in. There we go. There's a plus h missing. And what I have done is I've said, well, these h's cancel and this h goes to 0, such that we can have a record or the capacity to describe our gradient as accurate as we could make it by making that triangle particularly small. So that's what we're doing. The h goes to 0, close to 0. We don't want it to be actually 0. If it was actually 0, the triangle would just disappear. But we want it to be a small triangle so it's nice and accurate, leaving us with the equation of our gradient is change in y divided by change in x is 2x. And that is the conclusion that we can have at this point for a quadratic. Now, I want to analyze this a little bit further. There's our change in y divided by change in. For a quadratic, it is 2x. And remember, our quadratic is x squared. If it was a more complicated quadratic, it wouldn't exactly be 2x. But we can discuss that at a later date. Let us now evaluate or analyze what this means so that we can have a better understanding. So I'm going to take this in steps so that by the time we have finish this conversation, we perhaps will have a good understanding, I'll use the phrase understanding once more, of why we have an x in our gradient. Remember that when we did, for example, y equals 2x, the gradient was just 2, it was just a number. The gradient just represented how much does change in y change with x. Why do we therefore have an x when we do it for the quadratic? And here is why. First of all, let's think about this quadratic, the shape of it. When x equals 0, then it will be y equals x 0 squared. 0 squared is just 0, so we'd have the coordinate, we'd have when 0, 0 when x equals 0. Now what's the gradient at that point? What's the gradient at 0, 0? Well, the gradient will be 2 times 0 because x is 0. So we have to consider that if x is 0, then 2 times x will have to become 2 times 0. So there, if we have a gradient of 0, we can conclude that not only is the coordinates 0, 0, when we have the coordinate 0, 0 on the quadratic, the gradient is 0. What about when we have the coordinate 1? Well, when x equals 1, we'd have y equals 1 squared. 1 squared is 1, and so therefore we have the coordinates 1, 1. And this is the one that we've been particularly dealing with. As you can see here, this is the coordinate 1, 1. Let's make this clear. There is our coordinate 1, x equals 1, y equals 1, and this is the gradient at this point. We were trying to figure out what's the gradient at this point here. And we can work it out because we have to figure out, well, x is 1, so if I plug it into my equation of the gradient, it will become 2 times 1. 2 times 1 is 2, so the gradient is 2. What about when x equals 2? And by the way, we can probably see that is perhaps the case. This length, this change in y that we have here, this change in y here is double the size of our change in y, of change in x. So that seems to be depicting truth. Now x equals 2. When x equals 2, we'd have, of course, 2 squared, which is 4. And at 2, 4, the coordinates 2, 4 on the quadratic, the gradient will be 4. And so what you can see is why we have this equation for the gradient is so that we can work out the gradient at any point along the curve. For example, at 0, 0, you can see that there is no change in y, change in x. So at 0, 0, there is no gradient. The change in y is 0. 0 divided by 0 is 0, and so therefore it should be 0. We've already discussed what happens at x equals 1. We get 2. and the gradient seems to just be growing as it should do, because you can see that for a quadratic it's going to get steeper as you go along. It's getting more and more steep. You can see it's coming away from the triangle because it's becoming steeper. So to conclude with regards to this, the reason we have the gradient equation is so that we can work out the gradient at any point along the curve, because the curve has a changing gradient at different points. The gradient here is different to here, which is different to here, and is definitely different to this point here known as the minimum.